Hello everyone, hope you are doing good. So today's session, we're going to learn how to perform Gwas analysis by using Gapit package in R Studio. So Gwas genome-wide association studies has been widely used in plant science, in animal science to map the genomic regions, or in this specifically called as marker trait associations called MTAs for a particular trait in many crops. So in the GWAS analysis, the most important, there are very different models where you can perform the GWAS analysis. So today we are going to discuss about mixed linear models, that is MLM models. In the mixed linear models, there is a random effect and there is a fixed effect. So in the mixed linear model of GWAS, we will going to calculate population structure and kinship matrix. So the population structure is considered as fixed effect and the kinship matrix is considered as random effect. So the present video shows how to do GWAS for a trait known as 1000 kernel weight in wheat. So 1000 kernel weight is a weight of 1000 grains in the wheat, and we have a genotypic file of SNPs, high density SNP markers, single nucleotide polymorphisms. We have around 12,000 markers. And just to let you know, wheat is an X haploid. It has A genome, B genome, and D genome. The haploid number of chromosomes is 21, and each genome has 7 haploid chromosomes. So 3 genome A, B, D. So each genome has 7. 7 into 3, 21. So before going into this codes and Gapit package, I would like to show the phenotypic file, how it looks like, and what is there in the phenotypic file. So this is the phenotypic file in which I have given the data for 1000 kernel weight. This is environment 1, DF1 is a disease-free environment, and the NA is the it's not answered. The values are not known for that genotype. And here is the trait. The column name should be for the column name should be for the genotype should be trait. This should be fixed. A open arrow mark, trait, and closed arrow. And these are the genotype names. The same genotype names there in the genotypic file. So in wheat GIDs, especially this is from an international collaborative project where GID is known for genotypic identification number. So these are the 1000 kernel weight in the grams. Suppose genotype GID 8776489 as 42.6 grams as a 1000 kernel weight. So for Gapit model, uh, for the Gapit GWAS, we need to convert all the files into TXT form. So this is in the Excel form. So you need to prepare a input file that's in the Excel, keeping the A1 column as a trait, same as this, and you can mention whatever the trait you have here, and it goes till 1273 genotypes I have. So it goes till 1273 genotypes. Each genotype having is 1000 kernel byte. So we are going to convert the file into txt format, text format. So file, save as. So this is my directory gwas, convert into text ms dos. Yeah, this is as a pheno, save. So my file is saved now. So this as, I'll just transfer this to this. So this as phenotypic data and genotypic data. Unfortunately, I can't show genotypic data file here because the size is quite higher. So I can show you this genotypic data file in RStudio. So the basic codes for the RStudio for GWAS analysis. First, you need to download the Gapit package. So to download Gapit package, you should download DevTools. So this is the uh, code to download to install Gapit in the RStudio. So I'll paste all these codes in the comment box so that it will be useful for you. So install that packages, DevTools install. So this is the direct GitHub link where you can download Gapit 3 directly. So I'm giving here the GitHub link. So Geobo Wang Gapit 3, and I already downloaded it in my RStudio. So after downloading RStudio, just need to library it. Open the RStudio, open the Gapit file, Gapit software, sorry, Gapit package, and so usually nowadays Gapit 3 is coming like a Gapit. So you no need to type Gapit 3 here. Just put library and Gapit. So the package is open, and here you need to put the working directory path. So my working directory is this. So I'm going to copy the path from here and paste it here. And you need to change the slashes to right direction slashes. That's what R accepts. And so I said I just opened the Gapit package. Then I set the working directory, and I'll list the files which we have in the working directory. So there are three folders. One is three file, two files, one folder. There's a all folder which you are not interested in. There's the genotypic.txt and pino.txt. So these codes are default, common. So to read phenotypic data, my y, this should be the same for all the GWAS analysis in the Gapit. So my y, read the table. This is the file name pheno.txt, and headings, column heading is equal to true. So it reads column headings. In the genotypic file, myg read the delimited. It's also kind of table, and this is the file name genotypic.txt, and make sure the head is equal to false here. We don't want the column names to be read here. And the same the y, the phenotypic file is equal to my y, the genotypic is equal to my g. And the PCA, principal component analysis, this consider for population stratification. I already done population stratification by population structure, and I found two spikes, not three, two peaks, which suggests that in delta K statistics, two peaks suggest that there's a two population structure. I will also show when I get the PCA figure from this analysis how the two populations are clustering together. And the SNP marker allele frequency, the minimum allele frequency is 0.05. So we don't want any minimum allele frequencies which are less than 5%. So we want all the the SNPs which is having the allele frequency more than 5%. So model we are going to use MLM. So n.sig is equal to 20. It shows we need the PEV, phenotypic variance explained, for top 20 uh, MTAs, and file.output is equal to true. So initially I'm going to read the phenotypic file, control enter, click on this. I think you already know how to run the code in R. Just click on the code and press control enter. So we already got the phenotypic file. This is the phenotypic file, and we read the genotypic file now. It takes time because it's a big file, so it takes time. And this is the genotypic file. We have the SNP names, the alleles for these, and the position, and each genotype's allele at each marker, the SNP marker. So we have around 12,000 markers, and we run the Gapit software for MLM model. Just select everything and control enter. So it takes some time because it needs to calculate population structure, kinship matrix, and run the model, and need to calculate PCA. So this PCA dot total is dependent on your population. Suppose if you got three clusters in the population, then you need to set it as a three. If it's got four cluster in a population, then you need to set it as a four. So in my population, I just got two clusters. That's why I set PCA is equal to two. So PCA is setting PCA number is very important. So if we put wrong PCA number, then it may change the results. The results might be quite different. So you need to do either PCA analysis or population stratification analysis through structure harvester in TASL, and you need to identify the number of clusters. Then you need to use this in the Gapit software. I've been telling Gapit as a software. This is not a software. Gapit as a package using Australian. Sorry for that. And yeah. So meanwhile, I'm just enjoying my coffee. It takes some time. So all the files from this results or analysis will be saved in the working directory. So I will show what are the files need to be looked and how to uh, see the results file. What are the important files need to be considered, like a Manhattan plot, the PVE variance explained, and the PCA plots, and all the minus log 10 p values. It gives the p values, so you need to convert into minus log 10 p values. If anything is fine. So usually in GWAS we also use Bonferry corrections. Um, that's total number of genotypes, total number of markers divided by genotype. That's the formula for that. I think it's correct. Genotype, total number of markers divided by genotype. You can check it again, and you can set the thresholds. So usually more than five. That's what usually considered now. The minus log 10 p value is more than five is usually considered now, and more than p values in the GWAS, stable MTS are very important. The MTS, suppose one environment data is not enough for the GWAS. At least you need to have a two environmental data. So in the two environmental data GWAS, between environments, which market trait associations are common, which are appearing in both two environments, those are called as stable MTS. So those are very important. So and if those stable MTs having minus log 10 p values greater than 3 or greater than 5, so whichever threshold you want to set. But there are many uh, research evidence where the people have used minus log 10 p values greater than 3. 3 is a threshold. But nowadays, most of the GWAS is accepted for threshold of 5 or Bonferry corrections. So you can calculate the Bonferry corrections, then you can keep the threshold, you can keep the MTS, which is having minus log 10 p values greater than that, greater than Bonferry corrections, the Bonferry values. So I think you already know what is Manhattan Plat. So Manhattan is actually a city in US. So it has huge various number of tall buildings. So when you see the Jiva's Manhattan plot, you see the tall tapering S&Ps, so which looks like the Manhattan city. That's why it's named as Manhattan plot. And and if you have any doubts regarding this code, you can just comment on the comment box. And this I'm doing for my interest, and where I'm going to upload a lot of videos related to plant breeding analysis, genetics analysis, physiology analysis, quantitative genetics, and all kind of different analysis used in crop science. And yeah, so GWAS is done, and you just go to working directory. So this is the working directory, and you can see a lot of the files they have generated. So I will just first show the PCA plot where I will show the population stratification. This is Gapit genotype PCA 2D. So it's a two cluster. See, there's a one cluster of population here around this. Sorry, around this, and there's another cluster of population around this. So that's why I kept PC as two. And let's go for Manhattan plots. So the genome-wise Manhattan plots. So this is the Gapit association Manhattan plot. So you can see. So these are the chromosomes 1A, 1B, 1D, 2A, 2B, 2D. And this is the minus log 10 values. And you can see these are the SNPs marker trait associations. So this looks quite interesting because it's been tapering from bottom to top. This MTA is quite interesting. This SNP is quite interesting. And if you go to look the Gapit results, where it has the SNP and the p-values. So these are the p-values, and this is the SNP. So we need lowest p-values. So we can just go here, sort it from A to Z. So this is the lowest p-values. You can also convert this into minus log 10 values, log 10. The simple formula in Excel is equal to minus log 10. Just take the p-values. So this is 4.5. Just do something. So we can consider anything more than 3, or maybe this in this session, in this particular thing, we can consider anything more than 4. So these are the top 4 MTAs, which is having association with the 1000 kernel byte. If you check, there's a 1 on 1A and 3 on 4A chromosome. If you check the Manhattan plot, see, there's a peak on 4A, the 4A chromosome. There's a peak on 1A chromosome. So it represents the same. And if you want to know the phenotypic variance explained, so for the top 20 significant association, it gives the phenotypic variance explained. So this is not required. So if we take this one, it's a 0.8%, and this is the top one. Oh, sorry, this one is the top one. 1B87983 is 7.6%, and the p values might come somewhere. If I calculate minus log 10 value, minus log 10, p value might come somewhere 3.4. And for all 4A, there's a 0% for few MTS. The second one is 4A, 111087487. There's a 6.03% phenotypic variance explained. So we need to consider the MTS which has higher phenotypic variance explained plus higher minus log 10 p values. And more than this, considering MTS which are stable, which are appeared in all the environments is very important. So those are the real MTS because it has appeared in all the environments. So it has for for sure in stable association with the phenotype. And if those MTS come in the top 20, then you will get the phenotypic variance explained for that. So you can use this in the new result section. Don't say. And any other? I think most other things are not required. This it gives a descriptive statistics about all the phenotypic data, the distribution, the scatter plots, box plot, all the stuffs. And this is not required. It gives something about the SNPs distribution across the genome and the R-square values, the linkage disequilibrium values. And yeah, so this is the very important file, the result file, where you can filter out uh, the top important MTS. Just to make it short. So top important MTS. And this MTS can be further used by using International Wheat Genome Reference Sequence, IWGSC, or any genome platform. You can able to identify the candidate genes neighbor or adjacent to this MTV. So what should be the window to consider to consider the distance for identifying the candidate genes? So it should be the linkage disequilibrium values, LDDK values. If the LDDK value is 300 kb, then you can consider 150 kb positive, 150 kb upstream, 150 kb downstream from the MTA, and identify the candidate genes within this 300 kb. So this is for today, and thank you very much. Please like, comment, subscribe my YouTube channel, and let me know if you need any specific videos on genomics, statistics related to agriculture and plant breeding. Please comment on the comment box. I will make a video for that. Thank you very much.